Thank you for coming. I'd like to welcome again Chazelle from Princeton University and also Collège de France and Institute for Advanced Study, who came here to give us two talks. One of them was yesterday. We also gave a very long introduction. Today he's giving the second talk on natural algorithms. And the title is The Amazing Dynamics of Influence Systems. And without further ado.
Okay, thank you, Nir. Thanks for being back. And again, I want to say how pleased I am, honored, greatly privileged to be here to give this lecture, and especially to be surrounded by so many friends. And so I gave a talk yesterday. It was more general, and today I'd like to get down to more, some of the more gritty details about how this thing works. But before I talk about influence systems, I'm going to take a little excursion about exogenous systems. So there's this physicist whose name I will not attempt to pronounce. Only Dutch people can pronounce this name. Now, don't try it at home. It's very bad for you. See, it's very bad. It's very bad for your vocal cords. Don't want to damage this, and so. Now this is something that his legacy, see in Physics 101, put these three metronomes on 2 cans of Coke. Diet Coke works too, I think. But and then you let them go, and they have the same frequency, but they start in arbitrary phases, and sooner rather than later, they'll all be oscillating in lockstep. So they talk to each other, obviously. Now this is well known, well understood, but perhaps we can push this logic further, which this man did. A composer who did this beautiful piece about, now you thought metronomes were tools to help musicians play, but that's not what they are. They are musical instruments themselves. And so this is a piece for 100 metronomes. Sometimes people run out of ideas. And now this guy was an interesting explorer. And there he was in Thailand or Malaysia, and he saw this amazing sight. I'll show you the sight. These are like a gazillion fireflies flashing in synchrony across a whole river that stretches for miles and bent around and so on, so they couldn't all see each other. And yet he witnessed this. He was so amazed that he wrote it down and dispatched it back to London saying, "You won't believe what I just saw." And they did not believe him because he was known for getting really drunk. And when he was drunk, he just write anything. So it was dismissed for hundreds of years. So when you get drunk, you be careful. It might be a great loss to science. But what he witnessed was true, though. That's not an illusion. So let's explain what's going on, maybe a more abstract concept. I give you an infinite sequence of graphs. These are undirected graphs. And maybe they're giving ahead of time, or maybe not. Maybe they come online or something like this. It's completely arbitrary. But they're over the same labeled nodes. And the first thing you do is you embed the first one in space, in your favorite space, okay? And then for each graph in turn, you move each node as a convex combination of its neighbors, something we saw about a little bit yesterday. Okay, so this would be algebraically, you take V, each vertex becomes a convex combination of its neighbors, and you impose a threshold. These probabilities should not be, too close to 0. That's just a technicality. It's not that important. But, well, it is important. But. So visually, it looks like this. In parallel, you pick each node, you look at their neighbors, take the convex hull, you shrink it a little bit, about rho, and then these guys move anywhere it wants inside. Bingo. Everybody's going to do the same thing with their neighbors, all right? Am I making this noise? No. Oh, good. repeat for each node. So you get this lovely picture. This is the genius of PowerPoint. Look, I'll do it again. There you go. It's good things for flights to be delayed when you can do that. And on and on and on and on and on forever, so it looks like this. And if you wait, eventually they will congregate. Then they won't stop. This process never stops, but visually it just stopped moving. But macroscopically it's still moving, so you can define notion of convergence when they're all inside a ball of radius epsilon, then you have epsilon convergence. Sometimes they all get together into one ball. That's called consensus. And it's nice to know sometimes when you have consensus. So this process was known to converge under some conditions. But I showed a few years ago that actually this converges under all conditions. There are no conditions attached to it. You don't have to have any connectivity for this thing. And in fact, the number of non-trivial steps is bounded by this, which is optimal. Non-trivial steps, the number of steps is infinite because this never moves. So non-trivial means those that move by more than epsilon. So there's some visible motion. And this is optimal. So the main tool of this is the S energy, which I want to get out of the way, which is why I'll talk about it briefly now. It's a generating function. So here's what you do. These are embedded graphs. The first one is embedded, and then the others are embedded simply because you apply this motion to them. So what you do is you take the distance of each edge here, and you sum it up, you raise it to some power s. S is a variable. And then you just take the sum over all the edges of the graph. And then you sum over all times. This is an infinite series. This is a pretty scary one because it's quite likely to be infinite. In fact, certainly when s equals 0, you're just counting the number of edges, which is infinite. So that's easy. When s is 1, is the total edge length. Is the amount of ink you need to draw all of these graphs. There's an infinite number of them. And it's easy to see the only interesting cases are between 0 and 1. Outside of 0, 1 is not interesting. You can show this function is a generating function. It's actually a lossless encoding of the edge length. So you can invert this thing, okay, which is nice. In fact, it's what's called a generalized Dirichlet series. And I want to tell you, at least visually, that it resembles the Riemann-Zeta function. This is the Riemann-Zeta function, very useful in number theory, which if you decompose n into its prime factors, give you something like this. Now you can write this energy, S energy, as a sum of, these are stochastic matrices and these are vectors. I don't have to specify what they are. The point is visually they are very similar. They're sums of products of various objects. These are matrices, these are numbers, but at least that's why this function makes sense, for the same reason as the zeta function makes sense. Zeta function being the generating function of the prime numbers. In 2 dimensions, well, in all dimensions, for any n, you can ask whether this function has a continuation, analytic continuation in a complex plane, which is an interesting question to ask if you're asking for symmetries. And so, I don't know the answer, but for n equals 2, then yes, the answer is yes, and this is what it looks like in the complex plane. And you have an infinite number of poles along the imaginary axis, so that's very nice. So there are some structural symmetries in this object, but what really we want to do is bound that, over the reals between 0 and 1. So I showed the following: if s is equal to 1, this is bounded by that, and between 0 and 1, this is bounded by that. This is optimal. And this probably is not. This n squared probably could be improved to n, probably, but I don't know how to do that. Maybe you can do that. Now, there's a reversible case, which is very important because I mentioned that again, but all of Markov chain theory is contained, or at least all symmetric Markov chain theory is contained in this theory. So everything you're going to prove with the S energy should allow you to rederive any known fact in Markov chain theory. In particular, the concept of reversibility is very important in Markov chain. So it's very useful to define a concept of reversibility here, which would extend, which would strictly extend the notion of reversible Markov chain. And you can do that, I'll spare you the details, and you find that the energy is much better, it's much lower. You notice this is exponential in n. N is the number of agents, whereas here it's, well, it's polynomial because s is between 0 and 1. So again, you have this exponential polynomial, which if you know a little bit about Markov chain theory, you expect this. When things become reversible, then you have polynomial bounds on things like mixing and so on. To prove this bound, it's very useful to define another energy, which is the kinetic energy, where what you do now is you look at each agent and you look how much they move at each step. So for each agent, you just see the displacement, you take that mileage and you raise it to the power s, and you sum that up, okay? So when s equals 1, what you're doing is computing the mileage of every agent, the sum of the mileages of all the agents when s equals 1. When s is less than 1, then this is raised to a certain power, okay? Now, it turns out if you can bound this, you can bound the previous one. I'll spare you the details. So let's concentrate on this one, which is friendlier to, it's not as useful, but it's easier to tackle. So visually, this is what happens. G0, the contribution of the kinetic energy is this. You see how much they move. So they move like this. So you look at, that's the displacement. And you take this length to the power s. And then you sum that up for over all times. You know, so that's what you're doing. Can you bound those things? See, you don't compute the, you know, these trajectories are infinite. Okay, so if it converges, at some point it has to go into little spirals. I mean, you know, they're gonna keep going zigzagging forever. So this is the proof. It's very technical, as you can see. And so, so you know about amortized analysis of algorithms. So this is beautiful because the way dynamicists would handle this, would try to handle this, and I claim they couldn't, is by using Lyapunov functions. Whatever it is, you don't have to know what it is. But the point is Lyapunov functions cannot work here for all sorts of reasons. This proof is completely computer science-like, you see, and that's in many ways really the point of that I'm trying to draw, that tools like linear algebra and Lyapunov functions are just too crude. They're just too coarse. They're not powerful enough. Computer science theory in many ways is much more powerful. There's a whole theory of online competitive algorithms which has this amortized analysis. So here's what's going to happen. I want to see how much displacement each of these agents. Now here's what's going to happen. Each agent is going to have some money, and when they travel, they pay. It's like a toll. You know, they pay for the gas that they use while they travel, and they have to pay out of their account, out of their piggy bank. But sometimes some of them will run out of money to pay for the gas. So what do? Well, they simply borrow money from the bank. Well, how does the bank get money? Well, you see, sometimes you'll be riding along, paying out of your piggy bank, and your piggy bank will have too much money. So you don't want to travel with it, so you deposit the money into the bank. And then you design a whole economy where you have a trading going on, where the bank loans, makes loans and deposits and goes back and forth. Okay, so you have the proof, therefore, is an algorithm. It's a trading algorithm, which explains what are the rules of the game, where you're allowed to trade, what, when, how, and so on. And then the punchline is to prove that, one, you can pay for all the travels. Every agent can pay for their displacements. Number two, the bank never goes bankrupt. A bank never going bankrupt is totally unrealistic in the real world, as we know. But in mathematics, we can think of that amazing concept of a bank that actually is solvent.
And what is the initial amount of money that each agent?
Yeah, so we have to give a certain initial amount of money that is pre-computed. Yeah, so there's a formula, yes, which depends on the geometry. So this is a very good question. So there's, you have to design all that. But the point is the proof is an algorithm. This is really the key point. And second, a Lyapunov function approach would have a bank and nothing else. There would be no piggy banks. That's the whole point, okay? Putting those piggy banks means that now there's an entire economy. if you remove the piggy banks and you use Lyapunov functions, you have a communist system, which actually makes sense because Lyapunov, yeah. So, and as we know, it does not work very well. Okay, so now mathematically, these are all products of stochastic matrices, which are very interesting objects. There's a geometric view of them, which is, I think, worth looking at. So this is a stochastic matrix. You can look at it as a polytope in the following way. Look at the first row. So it sums up to 1 because it's stochastic. And you can look at this as a point in R4. So each row is a point. And so you take the convex hull. Well, this was in 2 dimensions, but I mean in 4 dimensions, but it looks at 2-dimensional. But you take the convex hull, and this is this. So each matrix, stochastic matrix, can be mapped to a convex polytope by this operation. Now, here's another one. When you take the product between 2 of them, then you go, well, what happens when you get a polytope? Well, what happens? How do you get this polytope? Well, what you can show is that this polytope associated with this, I don't know what happens to the polytope, because this one, oh, there, oh yeah. I guess there's a maximum distance, you have to be careful. No, there we go, there we go, there, see that? So this polytope fits inside the other. It's like Russian dolls. They actually fit inside the other. So it's smaller in some sense. So when you go P1, P2 times P1, P3 times, you get a bunch of polytopes that form Russian dolls. In fact, they all fit into one another. I didn't draw it that way because it'd be confusing. But so they all get smaller and smaller and smaller. Now, by the way, this is true. If all the PIs are the same, then you just have powers of matrices. That's standard Markov chain theory, okay? And you just powers of matrices, and these polytopes will just shrink. Fine. Now, I claim that every single instance of bounds on things like mixing times for Markov chains. But there's also a whole literature on so-called non-homogeneous products of stochastic matrices, which is what I'm talking about. You know, don't multiply the same matrix all the time, but vary the thing. So what happens to this object? All the literature on this tries to understand this process locally. It tries to argue, well, I know this is shrinking. There are many ways of measuring shrinking: the volume, the diameter, the spectral gap, which would be some average, or Lyapunov exponents. The point is that you try to have some kind of local measure of this. But this cannot work here. Why? Because there's nothing local about this. It could well be that your Russian dolls do not shrink for a long, long time. And I can give you examples of this. So any approach that is based on a theorem that says when you go from t to t plus 1, something good is going to happen, cannot possibly, must fail. Okay? It has to be global. And that is what the S energy does. You should think of it as like a Fourier transform kind of thing, except it's more like you fix a temperature. S is like a temperature, and the S energy is a number that measures something along an entire infinite trajectory of this animal. Okay. Now the question is to pick the best S possible for your purposes, which is often done in tail estimates or probability distributions, Hovding bounds, Chernoff bounds. When you think about it, it's always done in a similar way, though the functions are different. They're not Dirichlet functions. They're just exponential moment-generating functions and things like that. Okay? So the whole thing is this is an entirely global instrument as opposed to local. And number 2, the proof of how to bound them is inherently algorithmic. Okay? All right, so that's important.
When you said that the volume goes in, that each polytope fits into the previous one, doesn't it mean that the volume is a strictly decreasing function?
Not possibly, yes.
So why isn't the volume a good way to measure the convergence?
Because it doesn't tell you, it could be very, very slow. In fact, it does not have to be strict. It could stay the same for a very long time.
The same.
Yeah, it could be.
It will never increase.
No, it will never increase, but it could remain the same for a very long time. And it could also be 0 because it could be flat, but that you could change the dimension or something. So that's the problem, that with the volume, you cannot say from t to t plus 1, the volume has to shrink by so much. There's no bound on this, because I can show you cases where this bound is arbitrarily small. That's the whole point. But if you look at it over the entire period, like in an amortized, that's why it's amortized analysis. Because amortization is how you deal with infinity. It's how you deal with the entire global time scale, not just local time scale. That's the whole point of amortized analysis, by the way. Okay, so now this is all one-way, two-way communication. But what about one-way communication? You see, the graphs were undirected. What about the graphs being directed? This theory cannot work. I mean, you can prove by counterexamples this theory cannot possibly work, because there's no bound. I mean, for one thing, it doesn't converge. It could be a Turing machine and so, or something. So what we must do, that's what this influence system does, which is another way to look at it. The system I just analyzed is an open loop system. It's exogenous. The graphs can be anything you want. So it's very general. Now we have to look at endogenous, closed loop dynamical systems, which are entirely defined by themselves, which would be the standard dynamical systems of dynamics, okay? So that's what influence systems, I defined them yesterday, so I'll go very quickly, because now you're all the masters of this trade. So we have our friends here from left to right, and these are the political opinions. Okay, so there they are. And we have this communication graph, and it's defined in a certain way. Each agent has her own algorithm, communication algorithm, edge selection algorithm, which tells her who to talk to. Well, it's this one right here. Who to talk to, depending on the position in the state space of the object, of the agents, okay? So that is the edge selection algorithm, which can all be different, and which I want them to be very expressive. So, I mean, any algorithm you have in mind basically is acceptable. Basically, it has to be decidable, pretty much. That's all. So, I mean, in practice, in biology or something, there will be very efficient algorithms because you cannot wait forever for something to happen. But I don't require that, okay? So, for example, it could be like, so logically, you express these algorithms as solution of sentences like this for, you know, there exist y's for all y2. So, for example, join to the nearest neighbor. It's easy to see how you can express this in that language. Or join to agent j if there exists a wall such that for all ellipsoids there exists an agent k, such that for all simplices containing more than half the TSP edges, such that. Why would you do this? I have no idea. But you can if you want. Okay? That's what that language allows you. So it's very general. Now, all the algorithms can be different, and it also has an action algorithm. We'll just look at the diffusive case today, which means that the action will be like a convex hull operation, like we did previously. In other words, her algorithm tells her where to move inside the convex hull of these three people. All right? There we go. There we go. So it's very simple. All right? Okay. So it could be the mass center or other things. So this is called diffusive. So there you move, you form the graph again using the edge selection algorithm of each agent, and then you move again using their action algorithm, and so on and so forth. Now here's the thing, that these systems are almost always periodic, but occasionally they're not. Now, if they are bidirectional, they always converge. They always have fixed point attractors. In other words, if you have things like Facebook, this will always converge. So people on Facebook will eventually agree in clusters. But if you have one-way communication, like for example, newspapers, TV, I mean, those things, the radio tends to be one way. You don't talk back much. And there, things will not converge. Polarization will occur, but people will constantly change their minds. That's what this theorem is trying to say. Or at least in theory, that's what it's saying. In practice, that's something else. Now, to prove this, really, is using the S-energy argument that I just showed. You can use that technology if you know that the edge selection algorithms guarantee, you have an a priori guarantee that all the communication is two-way, then things will converge. But that's a restriction. So let's remove that restriction. Let's just allow the edge selection algorithms to be anything you want. Then you have this, okay? So let's talk about this. There is the word almost surely, which means there's some kind of probability measure, and the way we define this is by perturbing the systems themselves. Remember, these algorithms are defined the first order of polynomials. I mean, they're quantifiers followed by polynomial inequalities. Well, perturb the inequality by adding epsilon. Okay, that's it. That's what I mean by perturbation. Okay, so there's a little perturbation that you can do. That's what I mean by when you perturb this over an arbitrary small interval, minus epsilon 0, you will get asymptotically periodic with probability 1. And probability 0, but it can happen, could be chaotic or worse. And you know, this is chaos without positive Lyapunov exponents, which is very uncommon in dynamics. Well, okay, let's skip this. Now, I start talking about, okay, so now we're getting a little bit into the nitty-gritty, okay? What does it mean, this first order theory of the reals? Well, here's this picture that describes what it is. So I'm moving to phase space. What is phase space? Each agent lives in dimension d. So you need d times n numbers to describe the state of the system at any time. So phase space is r to the dn, okay? And a configuration of a given system is a point in the space, okay? Now, all these edge selection algorithms, which are defined in first order, they divide up that space by algebraic surfaces. There's all these algebraic varieties that just cut up this thing into cells, and within each cell, the graph is the same. In other words, any point inside that cell is mapped to the same communication graph. Okay, it's piecewise constant in this sense. Okay, and therefore, since you have this diffusion process, within each cell there is a stochastic matrix which corresponds to each cell. So, you know, think of this in 3 dimensions. Just divide up this room into chambers, and each chamber will have one stochastic matrix associated with it. You're all with me? Okay. They cannot be all different. All right? Now let's see what happens to the dynamics. If you start here, then you look up in which chamber you are, when you're in this one, and you look up what stochastic matrix is associated with it. And then what you do is you multiply it. I mean, this is a vector in that dimension. So you multiply this matrix by this vector here. And that sends you somewhere, like here, there. And to continue, you look up what stochastic matrix you have here, and you go there. You look up this one, and so on. This is how the dynamics goes. And you want to know what happens. Is it periodic? What happens? Now, as an algorithm, we have to study this in ways we people in algorithms are not used to. In other words, we have to look at what happens to all inputs at once. This is crucial. If you just focus on one input, you know, like you have a sorting algorithm, you look at an arbitrary permutation, and then you see how it gets sorted and try to bound the time. You cannot do that. You cannot focus on one input, on one trajectory. It's meaningless. It'll get you nowhere. You can only reason globally, but it would be like asking, take the entire space of all permutations, take quicksort. What is the first step? What happens to that space? You have to reason globally. There are deep reasons why this is inevitable. So you have to look at how these maps transform that space, okay? So instead of taking a point, now I have problem drawing, okay? Because I cannot show you how these maps transform the entire space, and it's too complicated. My drawing skills are not big enough. And so let's take one ball. This is a ball, And let's see what happens and why things can be complicated. Now, this ball sits nicely inside one chamber, and therefore, there's one stochastic matrix associated with it, so that entire ball is mapped somewhere through one stochastic matrix. That gives it an ellipsoid, but I'm not good at drawing ellipsoids, so it's just a sphere. Okay. Now, notice this sits in between two chambers. Okay, it cuts that algebraic variety right here. So the guys that are here are going to be sent according to one stochastic matrix, and the guys over there are going to be sent to another one. They're going to split up. You see what happens. So there's two of them here. And there we go. This one went over there, and this one went over there. You've got this split. Now, you're unlucky. That happens again. This guy falls into two chambers, two or more, and this one, same thing. They will split again. And there, my PowerPoint patience runs out, and so I just let your imagination figure out what might happen later. Now, you don't know what happens later because it really depends if you're lucky or not. When that ball flies over and lands somewhere, if it lands squarely inside a chamber, it's great. Next time, it keeps its integrity. Next time, it just flies over somewhere else. But if it falls right, smashed against this wall, then it gets split up. And intuitively, this is where things get messy, because they split up. That's how chaos grows. Okay? Now, that's one phenomenon, this branching. There's a branching mechanism. So let's try to formalize this a little bit. So you define the coding tree. If you do symbolic dynamics, you do a lot of that sort of thing, representing trajectories by strings. So this is my best impression of this picture here is this. It's not flattened, that's just what it is, because I have only 3 dimensions to play with. Actually, I have only 2 dimensions, but so this is this. This is times 0, okay? And this is this. And I take all the maps, and you see why there's this inherent branching process. So it's easy for you to imagine that the map will produce this tree. This is a real tree in the sense that it's like a tree you see outside. It has volume. It's not a combinatorial tree with just... This has actual branches and volumes and so on, okay? In particular, like here in the base, you will have each chamber. Each of the original chambers will be, the root will split into the original chambers. And then each chamber flies somewhere and then gets split up into more. These branches may overlap, of course. I mean, they might cross each other. Why not? Okay? So it's a bit hard to visualize those things, but there it is. Yeah.
I think that I lost the picture, so let me ask you questions again.
Yes.
I don't know if it's only me. So the earlier picture, the chambers are nothing. Let's go back to the graph.
Yes.
What's the exact? So you said that the first order formula.
Yes.
Describing what the process that you do on the vertices, or they move, or what is the so then you get the polynomials, and I guess that these are the zeros of the polynomial.
No, okay, so let's start from the beginning. You're at time t, and you want to know what is the graph? What is the graph? Well, it depends on the position. Can we partition the set of all configurations into chambers that have the same graph?
So configuration of what?
Okay, so you have n agents. Each one has d numbers, d coordinates. A configuration is a string of d times n numbers. That's one point, yeah? That's a configuration. Now, with that point is associated one graph.
Given by the first order formula telling you...
Yes, given by the first order, yes.
So the formula is which are its neighbors, or
Yes.
or what is the cell, what is the convex cell into which
Yes. Yes, but you have to take all the algorithms for all the agents to produce that because you need to know the neighbors of every agent. Okay? And so that divides up space into chambers, and within one chamber, you have exactly one graph. It's a discretization of the problem. Yeah? With one graph, once you have a graph, the action algorithm tells you you essentially have one dynamic. So you have one stochastic matrix. Yeah? Did I answer your question? Okay, thanks for asking it because I think it probably helps.
I have a question about this thing.
Yeah, so this thing now.
Time should flow in one direction.
Yes.
So why are the branches of the tree always...
Here's the answer. Because I spent an hour on Google Images and I could not find a damn tree that had branches that did not go down. So you find me a tree with the branches going up.
Okay. So it's...
This is a touchy subject. I know they go down. I don't know, blink or something, and maybe put on glasses or something. Maybe they won't go down anymore. But yeah, they should go up. They should all go up. Yes. Yes.
The time should also be discrete, right?
It should be discrete, yes. It should be 1, 2, 3, 4, 5. Yes, you're right. Please keep throwing mud at me. Go ahead. I like it.
You can ask someone to
Maybe you don't like the colors. No, don't you think this is a little too dark?
No, we only want white and blue.
Yeah, white and blue. Yeah, well, there's a lot of white and blue. Now you're picky. Yeah, Ruben.
use someone to draw it with MATLAB, such a fractal. It's not a problem.
You know what?
A good, smart Princeton student.
This would be a good homework assignment, Ruben, for your students.
For my medicine.
Yeah, your medical student, your psychiatric students. Yeah, I think that they have a field day.
Describes how a chamber goes to a different chamber. What?
Yeah. So now, do you want to go back to this? What is this thing here? The picture is terrible, so I apologize. Okay. The first floor of this hotel, this discrete thing, has the chambers which are this. Okay. I'm sorry, it's just like this. Now, think of the root as being here, as being below. The first floor, you got all these chambers. Now here's what I'm going to do. Each chamber has one matrix. And so I'm going to follow that matrix. And that's the branch. These are the branches. Okay? This chamber goes to here. Okay? And then here they split. Because that chamber would fall between two original chambers, because the splitting is given by the first level of chambers.
Something is misleading because the chamber jumps. It's not a continuous movement, right? It's like
I think he's already made that point, yes. No, I can take the abuse, but yes, it is discrete.
No, it's not about this. It's not discrete. It's not what I'm saying. It seems that the chamber goes
To a random location.
It just goes,
Yeah.
jumps. It's not going to somewhere close to where it is.
Why should it? I mean, you multiply a convex set by a linear map. It could be very far.
No, it's okay.
The
No, it's just
discrete is the end rate.
Never mind.
You should have found a tree and Google project where the branches
No, no,
just...
it's okay. No, never mind. I'm okay.
No, the branches could be very long. I mean, these could be over here. I mean, there's no, these are just maps. The maps can just go all over. Okay? Yeah?
You keep telling me it can fall between two chambers, but it can actually fall in a high number of chambers.
Oh, yeah. Oh, yes. Yeah. It could fall into all of them.
Yeah.
Yes. Yes. Yeah. Ron.
So you want to do something a little crazy, like embed this in branching time, like physicists like to do.
Yeah, something like that. Yes.
It's a different dimensionality.
Yeah, but probably that's one way of looking at it. Yeah. Yeah. We'll see if I have any time left. So, if you climb this tree, like I saw a cat do that when we had lunch. Remember? The cat was going up that tree. And the first branch, it went one stochastic matrix to the next chamber and another one, and so on. So there's a sequence of stochastic matrices as you go along each branch. Yeah? All right, good. Now, there are two important. Now, this tree, you all agree, captures everything, up to perturbation. Fix the perturbation once and for all. This tree captures absolutely every question you can ask about the system. can be read off that tree because there's no information lost for any input. Okay? Now there are two important variables about that tree. One is the branching, how much it branches, because intuitively chaos is going to come from a lot of branching. And the second is the volume of the branches. The branches are going to shoot thin out, and we'll see why. And so it's going to be this competition between the energy, which in physics, the energy would be the thinning of the branches. They get thinner and thinner. They lose energy. So they go to a minimum energy state. Okay? They minimize the free energy. And the branching, which is the entropy. Entropy is brought into the system. It's this competition that defines criticality. Criticality means when you have a tie between these two forces. On one side, you have chaos in Turing machines. On the other one, you have periodicity. Okay? So we have to understand these two things. So branching, you want to show that if you perturb things a little bit, you perturb this tree, the mean degree as you go up the tree goes down. Or at least, okay, it can be complicated functions, but roughly you want to have a handle on the mean degree. All right?
You mean that if you move to a if your image is in the union of 7 cells, that's a degree?
Yes, yes, exactly. Yeah, the degree is essentially.
How much cells do we need to cover the image?
Yeah, when this chamber moves, how many other original chambers do you hit? That number, which could be huge. By the way, it could be exponential because the number of chambers is exponential. So the degree could be exponential. Okay? But to get a sense of what does it mean to branch analytically, well, start with a little ball, a tiny ball, and to branch means that you're going to fall. Here there's going to be a branching. So algebraically, what it means is that this set is the image of that ball through this matrix. So it's some ellipsoid of some kind. Now, to say that there's a branching means that it cuts this algebraic variety. That you can write polynomial inequalities. So there's a certain set of polynomial inequalities, and you can always express it that it contains 0 even only if there's a branching. Okay, this is a so-called semi-algebraic set, a real semi-algebraic set. So you can characterize this like this. Now, when you have more branching, more than one, along a certain path, then you're going to have a whole system of things like this. And what they have in common is that these are products. You know, you start with this one and you multiply it, multiply it, multiply it. So it's not completely arbitrary. And you want to show that these matrices, because they're stochastic and they have the same prefix, good things happen. All right? Well, this is, so you have a semi-algebraic set. But if you look at the structure, there's an inner tensor structure. In fact, this is generated by a tensor products. So by a certain tensor lifting, you can actually make this linear. And once you have linear system, you can do linear algebra. Okay, I said you wouldn't do it, but here you have to do it. And with some combinatorial argument, you reduce this to what's called matrix rigidity question in circuit complexity. Okay, it's basically statements about the rigidity, the rank robustness of certain matrices. It's combinatorics and linear algebra. And that will show you that the branching is not too bad. All right? Let me just skip that. That's all I want to say about that. Because it's kind of boring. I mean, it's just doing the grinding combinatorics, okay? The thinning actually is the more interesting part, okay? These trunks, these branches become thinner and thinner. They should. Why? Because physically, this diffusive process from an energetic point of view corresponds to damped couple oscillators. This is as though you had springs. These are one-way springs, by the way. They're not two-way springs. They're one-way springs. And the whole thing oscillates and finally comes to rest. And that energy goes down. This is exactly, that loss of energy corresponds to the thinning of the branches. And that's what you have to understand. Now, there are problems with this. For one thing, these cross-sections will become thinner and thinner, but not in all directions. Why? Well, you know, all stochastic matrices have the eigenvalue 1 with the same eigenvector, 1, 1, 1, 1, 1. Along direction 1, 1, 1, 1, 1, there's no shrinking because it's the identity. So these branches, are, at least you know, are not going to thin in all directions, not in that particular direction. But it's worse than that because that principal the eigenvalue 1 could have very high multiplicity, and that's is really the point. So that space could actually be, which is unattractive, could have high dimension. So it could be that this thins out. As you go up the tree, this is as you go up the tree and you see the cross section of the branch. Like the cat is going up, looks at cuts. Cats don't cut trees, but beavers cut trees, and just see how much. That's what it is. So this is an attractive manifold, because it's attracting because the springs will eventually come to rest. Okay. And this is like the principal mode of the system. But the problem is that the directions could change as you go because the graph changes. See, this is why Markov chains are so simple in comparisons, because Markov chains, those modes don't change. Okay? But here they can constantly change. So now, what are we trying to generalize? When you have a hard problem like this, the question you have to ask is, what is this a generalization of? Is a generalization of the following thing. Take a fixed graph, not necessarily undirected, so it's a directed graph. Take a fixed directed graph and do random walk on that. All right? Do a random walk. Now, in this case, for example, if you do random walk, sooner or later you will land either here or there. And once you're there, you can never escape. That will always happen. Just look at it visually. So these are attractors, okay? Because you always end up there. And the dimension of the attractors is 2, because she's an attractor, and these two will get together because this is undirected here. And so they will come closer to each other because they're attracted. There's a spring. And so pretty soon these two of them will be completely confined into one. And so there's only one dimension. So the dimension of the attractor is 2. And it's easy to show. I mean, there's a classical theorem that that dimension is essentially the number of so-called essential communicating classes of the Markov chain, which, in other words, are these two subsets. This is when the graph is fixed. And if you want to understand this shrinking, you really have to understand this attractor. Now here it's easy because it's fixed. The problem we have is that this thing changes all the time because the graph changes all the time. It could be there are the attractors, and then over there there'll be the attractors. They just keep on changing, which is why in the end maybe nobody will be an attractor, but you can have cycles. Ron, you had a question.
Yeah, a couple of slides back you had the diagram thing. You have a matrix at some point where you can make all kinds of games within algebra.
Yeah.
The question is, can you also play John Kleinberg style games with eigenvalues?
Yes.
Identify hubs and authorities.
Yes. So the answer is you could try, but it would not work because John Kleinberg cannot handle dynamic changing graphs. Once the graph changes, the eigenvalues are useless. That's the whole point. You know, this eigenvalue decomposition makes no sense. That's really what we're trying to wrestle here with, because over here you're okay. You can do spectral analysis, but as soon as this thing changes, you're dead. Okay, so what do? See, you need to understand how this attractor changes. So to do this, we sort of do what's in physics called renormalization. Okay, so let me introduce an algorithm that's very important. It's a very simple algorithm, but it's critically important for this analysis. And by the way, this algorithm is really the one I was telling you yesterday, where you try to understand the spectral proofs, why you can decompose operators and eigenvalue modes and all that. And then when it doesn't work because the graph changes, then you say, aha, it does not work. But perhaps I can extract something out of that and turn it into an algorithm which will then generalize it greatly. Okay, and this is what we're going to do here. So this algorithm goes like this. All these agents want to learn a song. The dog, of course, knows the song. Anybody who listens to the dog learns the song. So the doctor will learn the song in the next step because he listens because of this edge. But the cat is not listening to the dog, so the cat would not learn the song. So let's see what happened the next step. Well, the next step, you see this has changed, so the cat learns the song, and then she will learn the song from him. So you can never, once you know a song, a tune, you don't forget it. So this process can only, is monotone, increasing, all right? So if you keep on going like this, you will see she'll learn the song, you know, the song gets propagated. And here, finally, she learns the song, and now everybody knows the tune. This is great. Now when that happens, I'm not making this up, by the way. When that happens, that branch shrinks. You can prove that, okay? There, it shrinks. Now, here's the problem. How do you know everybody gets to learn the tune? It could be that he knows the tune, the cat knows the tune, she knows the tune, he knows the tune, and then you continue and she knows, but it could be that for a very long time, nothing is happening here. All these edges are going in that direction, and so nobody here is learning the tune. You don't know what's going to happen in the future. You're not a prophet. You don't know what's going to happen. Maybe it could be that they'll never learn the tune. Or it could be that you wait 2 centuries, and after 2 centuries, she decides to listen to him. And then she learns the tune. You don't know ahead of time. This is very important. When you do renormalization in physics, you actually know the decomposition ahead of time, but here you don't. All right? So you have to be prepared. And here's what you do. You say, well, I don't know whether they will learn the tune or not. So let's say that they learn the tune at time t1. T1 could be infinity. So you set this as a variable. You just don't know. Between now and t1, they're not learning the tune. So you can treat this recursively, separately, because nobody here is paying attention to what's outside. And therefore, you can treat this recursively, like a recursive algorithm. Or at least you can do this until time t1. But t1 is a variable. You don't know what it is. So it's a little bit chicken and egg thing. But you just stick t1 as a variable. Now, what about those guys? Now, this is trickier. You would love to say that you can also treat them recursively until time t1. But that's not true, because they are listening to these people. And therefore, their dynamics here is certainly influenced by these people. So you cannot simply cut the graph into 2. You understand? These do not influence these until time t1. But these do influence that. However, because the communication is only one way, until time t1, there's no communication from here to here. I mean, the arrows do not go from here to here. Then you can do something. You can do coarse graining. You can replace all of those guys by one super agent. And the reason is that, here's the reason. These people can influence these, but there's no feedback loop. These cannot. So the information cannot cycle. This is very important, because it's like a one-way cut. The information cannot cycle. So you can actually coarse grain all those guys into a super agent. And now what you've done is the following. Your system until time t1, which is unknown, is decomposed into one system that's completely independent. You can treat these totally separately. This one also, except for the fact that this is a coarse-grained version of that. Okay? So they're not completely independent, but the dependency is under control. You know which direction it goes, and this is a much simplified version of that. That's the whole point. If this was not simplified, there would be absolutely no purpose doing this thing. Ron.
So that we use some kind of macro
Yes.
or an abstraction of what you had there before.
Yeah, so
How do you extract the interface with the rest of the world?
I'll get to this. This is difficult, but you call that a goose.
Don't make it too difficult so I can understand.
Is this a goose? Let's take a vote. Is this a goose or is it a duck?
The goose.
It's a goose?
The goose.
It's the goose. Who votes for duck? See? Okay, all right. Goose probably wins. You win, Ron. Because some people get confused. which is stupid. It's not exactly germane to the problem.
You know, it walks like
It was like a goose. I will put a soundtrack on this. Excellent idea. Now we will bound T1 steps recursively. I cannot show you how to do that. But here's the thing. After T1, the communication resumes between the goose and the rest. So, oh yes, this operation looks like a direct sum because it is a direct sum in a tensor sense. So we can define a tensor addition among these coding trees where you take this, you add two coding trees, and you get this is like a product tree where each branch here is the product of two branches there, okay? So now when the propagation resumes, then what happens is over time this moves because this is between time 0 and time t1. At time t1, this tensor operation stops because the two systems start talking to each other. And so let's say that you have resolved what's happening from here to infinity. These two guys have to connect one another. But now they're connected through not a tensor addition, but a tensor product. Because these coding trees now are, I have a picture to show you what happened. And this is the renormalization step. What the direct product does is this. You have a coding tree and you have another one. And you take it and you glue it here. And then you do it for all the others. But I couldn't do that. It's too tiresome. Okay, that's the operation. This is not commutative. The direct sum is commutative. The direct product is not commutative. Okay, because this is time. Now, what do you get? You get an arithmetic in a certain language of tensors, which has more than just the two operations that I showed you. There's some others also, time scaling, for example. So you have this language which allows you to write the entire coding tree as an arithmetic expression in that language using variables that are unknown, because I still don't know what T1 is. I have to put this as a variable, okay? Okay, so I'll get to this. Here's the point. I don't have to go into the details. Here's the point. This coding tree, which you're trying to understand, which is this infinite tree, you can write it algebraically as an expression of objects. These are subtrees defined recursively. So this is recursive in many ways. Okay, these are recursive things. And then you have these operations. And then you have all these unknowns. Like all these things are unknowns. TK plus 1. These are unknown critical times where things happen. Okay? So this has lots of unknown, but still, it allows you to write this into this language. What's the point of doing that? Because visually, here's what you're doing. There's this unknown tree, which is very complicated, and you want to cut it up into sub-pieces to analyze. But this is a tricky thing. You cannot simply take your tree and cut it up and just take each thing. You see, this tree is formed by tensor operations of various kinds. So it's like Legos, where you could do tensor products and tensor things on Legos. Now, there's this unknown tree, and this is telling you that this tree actually can be built by Lego operations, tensor operations in a certain way. And this will tell you how to do it, okay? But you're going to say, okay, this is great, but I still don't know what these variables are. So what's good to do that? Here's the punchline. This is you can think of this as a circuit, okay? You can read this as a circuit because this is recursive. So you could actually have a circuit that feeds the answer to this thing. When you parse it, this gives you a recursive decomposition of the entire thing. And now you can start setting up recurrence relations among these various parameters, because these parameters will be related to the tk plus 1. So you can write these recurrence relations, okay, to do all that. And then you have a dictionary of bounds that tell you the following thing. If I have a tree A and I know the entropy, and I have a tree B, I know the entropy. What happens to the entropy of the direct sum? What happens to the entropy of the direct product? And so on. And therefore, so now you see the trick. You have this very complex Lego construction. You want to know its energy and its entropy. You have these decompositions in a certain way, in this tensor decomposition, and the elements, the unit blocks, you know their energy and their entropy. And you also know, when you take two of these guys and you do a tensor product, you know what happens to the energy and the entropy because you have this dictionary. In other words, you have a homomorphism between that Lego construction and the language of entropy and energy. And you know, entropy and energy are technical terms. In dynamical systems, you can have entropy. You know, the topological entropy is well defined with that randomness. So, you know, this not I mean, these are not impressionistic words. These are actual words in that thing. And again, if energy decays faster than entropy grows, the system is asymptotically periodic. That's exactly what you're trying to establish. And you show that by perturbing things, then this will happen with very high probability. So, I mean, in 1 hour, this is pretty much all the technical thing that will fit in 1 hour, and then it gets more technical. But still, I think pretty much the ideas that matter are all in here. Everything else is just cranking out the computation. Okay.
Can you show the theorem which was before this slide?
Yeah. So diffusive influence systems are asymptotically periodic almost surely. All right. You always eventually are trapped into an infinite loop. No matter how smart we think we are in learning the world and so on, we're trapped. We're doomed. That's one way to look at it. But unless you are in these critical perturbations, in which case this is like paradise, you become chaotic. Well, chaotic is paradise, but you become a Turing machine, which is our ultimate dream. I'm sure how many of you have so many dreams of morphing into a Turing machine. I mean, does life get better than that? Okay. So, and if they're bidirectional, so anyway, I have a little more, you know, there's a moral of the story here, is that not only I want you to study natural algorithms and convince yourself there's really nothing else worth studying, but also that in order to study natural algorithms, what you need to learn is algorithms, because these are the tools to study natural algorithms. Is algorithms, because the proofs are, I mean, there's some linear algebra, but that's not interesting. The really interesting part are actual algorithms. Trading, you know, I talked about setting up an economy and amortization arguments. I talked about my flow, my songs going around the system and people learning tunes and all of that. That's what I'm talking about, all right? So I will stop now. Thank you.
There are books that have been written about convergence of products of matrices.
Yes.
Are you ready to? Are you capable of reproducing those results from this general way of studying, or is the new way of studying products of matrices?
Yes. So yeah, for example, you're probably referring to, there's a book by Seneda. This is a classic book by Seneda on things. So the answer is the following, that there are two kinds of products. They're similar, but they're not totally different. When you multiply to the left or you multiply to the right. Here I multiply to the left. It's a little easier, actually. And in that book, there are results on both kinds of multiplication. Here I only deal with multiplication to the left. And there, yes, I can reproduce every single, I mean, this completely subsumes the entire book, that part. And much more than that. I mean, this gives you actual bounds. I mean, quantitative bounds.
You can get conditions on the because I think what they do is they give you a condition on some properties of these matrices. So if the matrices are selected from this and this set, then their infinite products are going to be convergent.
Yes.
They can say maybe something about it.
Yeah. So these conditions are much too strong. The thing that you can show here is that you can relax this condition enormously. They're much too stringent, so you can have theorems that are much more general than that. And the right word matrix products, I've never looked at it, so I'm not sure.
More questions? So Bernard is here until tomorrow. And thank you.
Thank you. It was my pleasure.